Hey guys, Miss Peterson here, and welcome to Stoichiometry Made Easy. I'm going to teach you guys how to use this mole map to solve any sort of stoichiometry problems with confidence. Now, I know math used in chemistry is sometimes one of the most confusing concepts in chemistry, so hopefully this lesson will make it a little bit easier for you. And if you want a hard copy of this mole map, it is linked in the description. So, before we get started on the mole map, I want to review something else, something called dimensional analysis. Okay, now dimensional analysis is a way of solving problems by focusing on the units. So every single time I do a problem using stoichiometry or using any sort of conversion factors, you're always going to start with your known. You can also see this as your given. Okay, and you'll want to write it. Let's say that my known was 45.0 grams, okay? And I wanted to convert it to milligrams. Now, you're going to use conversion factors. And conversion factors are equalities, okay? Things that are equal to each other that relate your known to your answer or your unknown. So if I wanted to convert from grams to milligrams, I know that there are for every 1 gram, there are 1,000 milligrams. So I'm going to multiply it by that conversion factor. My gram and gram would cancel out, and I could stop and have my answer in milligrams. Now, say I decided I didn't want it in milligrams. I want to use the density and find it. And I'm talking about seawater, which has a density of 1.1. I'm going to need something in milligrams. Let's see, what's a density of something in milligrams? Let's go with this hypothetical substance has a density of 0.30 milligrams per milliliter. Sure, why not? So I could use that as another conversion factor. I would want to cancel out my milligrams, and I would put 0.30 milligrams on the bottom per milliliter. When you say per milliliter, how many milliliters are you talking about? You're talking about 1 per 1. Miles per hour is miles you drive per 1 hour. Okay, so per 1 milliliter. So then I could cancel that out and have my answer in milligrams. Now, plugging this into the calculator, it would be 45.0 times 1,000 over 1. So 1,000 over 1 is just 1,000 times 1 over 0.30. Or you could just think of that as divided by 0.30. And we would get something like 1.5 times 10 to the negative 5. Okay, again, not a super great example there, but showing you how this works. Now, another example, we can look at converting centimeters from centimeters per minute to meters per second. So I'll go ahead and give this a number. Say it's like 5.2. That would be my known. 5.2 centimeters per is divided by. So per 1 minute. Okay. And then if we're doing conversions, I know that 100 centimeters is 1 meter. So 100 centimeters would go on bottom and 1 meter would go on top. And then I know that 60 seconds is 1 minute. Since I want to cancel out the minutes, I'm going to put the 1 minute on top and 60 seconds on the bottom. So then I have 5.2 over 1, so 5.2 times 1 over 100, or divided by 100, times 1 over 60, or divided by 60. And we get a really small number. It is 0.000866. So probably not the units we would use it in, but we can see how that conversion factor works. Now, another thing with this is scientists are lazy, and I don't like writing times and then parentheses and a line, and then times and then parentheses and then a line. It's just too much. So instead, what you will often see, and what I will be doing throughout this lecture, is doing a shortcut, which is like the train tracks thing. Okay, so it's just a shortcut for times and parentheses. and times and parentheses. Okay? But again, remember, all your conversion factors are always equalities. Okay? So let's go ahead and start applying this to chemistry. Okay? If we look over at our mole map, okay, what this does is show us how to relate different substances. So when we're talking about a sample, we could talk about its mass in grams. Now, moles is the counting units, how we count atoms, so that's our central concept. So to get from mass to moles, the conversion factor we use is molar mass. And how you set up that conversion factor is shown here, with some number of grams over 1 mole. And that number is the molar mass, which we use the periodic table to find. Okay. Then we'll have particles. Particles can be atoms or molecules or ions, basically anything you're trying to count. And to convert that to moles, we use Avogadro's number, 6.02 times 10 to the 23rd. And then if we're talking about a solution and a volume of a solution, to relate that to moles, it's the molarity. Molarity is the concentration of a solution. So something like 3 molar NaOH contains 3 moles of NaOH per 1 liter. 2 molar H2SO4 contains 2 moles of H2SO4 per 1 liter of solution. Okay? Then the last thing we have is moles of A to moles of B. When we write our chemical reactions, like say we're writing, we got aluminum. I'll go ahead and write a reaction that we'll use later. We'll have aluminum reacting with copper chloride to produce aluminum chloride and solid copper. Gonna go ahead and, oh, there's a 2 there. Gonna go ahead and balance that reaction with a 3 and a 2 and a 2 and a 3. Now, those 2s and 3s represent the mole ratios. This reaction reads 2 moles of aluminum react with 3 moles of copper chloride to produce 2 moles of aluminum chloride and 3 moles of copper chloride. They're that ratio. Those are your coefficients. And those are the only 2 things you can use to relate the moles of one thing to moles of another thing. Okay? So, we'll go ahead and use that reaction. I'm going to go ahead and put that reaction up top, and we'll use it as the basis for the rest of our problems. And that was 2, we'll write it a little bigger. We got 2 aluminum plus 3 copper chloride reacts to produce 3 moles of copper and 2 moles of aluminum chloride. Okay. So let's go ahead and start with a 1-step conversion. Now, a 1-step conversion using something like this, aluminum is normally as a solid. So if we are talking about aluminum, we might weigh it out on a scale and say I have 2.85 grams of aluminum. Now, if I wanted to convert that to moles, how would I do it? Well, we're going to be at grams up here by mass, and we want to get to moles. So we're going to be using the molar mass. And if we look at that molar mass, we're going to be going from grams as our known to moles. So the conversion factor we'll be using is 1 mole is some number of grams. Okay, so if we're setting up dimensional analysis, we always start with our known, 2.85 grams of aluminum. And then this tells us our conversion factor. It is 1 mole over some number of grams. Okay, and that number is the molar mass, which we use the periodic table to find. So I'm going to go to my periodic table, find aluminum, it's number 13, and it has a mass of 26.98. So 26.98 grams. So the grams will cancel out. I got 2.85 divided by 26.98. So 2.85 grams of aluminum is equivalent to 0.105. So I'll go, or 1056. So 106 moles of aluminum. Okay, cool. Okay, cool. let's go ahead and look at another one. Okay. Now, copper chloride normally comes in a solution. So, if I want how many liters of a 1.5 molar copper chloride solution would contain, let's say we need 2.5 moles of the copper chloride. Okay, so this one might be a little bit confusing because we have two numbers that we're given. Which ones are known and which one are we going to use as a conversion factor? Well, our mole map can help us with this too. These purple ones are always going to be either our knowns and our unknowns. That's going to be where we start or end, either at the moles or at one of these purple ones. These arrows are the conversion factors. So since molarity is a conversion factor, that tells us that this 1.5 moles is going to be used as a conversion factor. And we're actually going to be going from moles as our unknown to liters. So moles right here is our known, and our unknown is liters. So we'll be using that conversion factor. I'm going to come down here to solve that so you guys can kind of see what we're doing. But again, our known was 2.5 moles. Okay, so that's my moles. And then if I'm going in this direction, I want to get to volume. The conversion is 1 liter over the number of moles, where that number is the molarity. And the molarity they gave us was 1.5 molar. Okay, 1.5 moles per liter. So then I got 2.5 divided by 1.5, which gives us 1.66666. So we'll go with, we would need 1.67 liters, or we'll go with 1.7 liters. 2 digits in my known, 2 digits in my unknown. Okay, cool. Okay, cool. Let's go ahead and try some 2-step conversions. Okay. So for our next problem, we're going to go ahead and incorporate this mole ratio in the balanced chemical equation. So let's say that 1.04 moles from our previous problem of the aluminum react. How many grams of copper could be produced? Okay, well, we are now starting at moles, okay? Moles of aluminum is going to be our known, okay? We got 0.104 moles of aluminum. Yep. And since this is going to be a 2-step problem, I'm going to need a little bit more room. So I'll go ahead and do it in this middle area here. So we got 0.104 moles of aluminum. Okay. Now we want to get 2 grams of copper. Okay. Now copper is going to be our unknown. And our known, we're talking about aluminum. So if we're anywhere on this side of the mole map, we're talking about aluminum. Where if we're anywhere on this side of the mole map, we're talking about copper. Now the path that we're taking, well, our known is moles. So we're going to be starting right here at moles of A. We'll use the coefficients in the balanced chemical equation to get to moles of B. And then we want to get to grams. So we're going to have to use the grams per mole, that molar mass of copper, to get to grams. Okay. So starting with the coefficients in the balanced chemical reaction. We're talking about our known, which is aluminum, has a coefficient of 2, and copper, which has a coefficient of 3. That tells us for every 2 moles of aluminum that react, we will get 3 moles of copper. Okay. And now we're at moles of copper. We got one more step, which is the number of grams per mole. And again, that's the molar mass. So the molar mass of copper is 63.55 grams per mole. That's going to go on top. 63.55 grams of copper is 1 mole of copper. So the mole units cancel out, okay? And the work that we have is we got 0.104 times 3/2 times 63.55, which gives us an answer of 9.91 grams of copper that would be produced. Okay, cool. Okay, cool. Let's try another two-step conversion. So we're going to go ahead and try this one, which says how many atoms of copper can be found from 3.2 grams of copper. Okay, so we don't have a known and an unknown here. We're talking about copper all the time. So we're going to be staying on one side of the mole map. Atoms is particles. So this is going to be where our answer is, our ending point. And then we have 3.2 grams of copper. So we're starting up here with our mass. So we're going to have a two-step conversion where we're first going to use the molar mass to convert to moles. And then we're going to use Avogadro's number to convert to particles. So just like every other time, we start with our known, 3.21 grams. We're going to use the molar mass, okay? And we're going in this direction to moles. So it's 1 mole over the number of grams, which is the molar mass of copper. We already found that. It's 63.55 grams. And then we'll use Avogadro's number going in that direction, which is 1 mole is 6.02 times 10 to the 23rd particles. So again, the gram and gram units cancel out, mole and mole cancel out. We got 3.21 times 1 over 63.55 or divided by 63.55 times 6.02 times 10 to the 23rd, which gives us 3.04 times 10 to the 22nd atoms. Okay. Oh yeah, we should be specific. Particles, we're talking specifically about atoms. Okay, cool. Okay, cool. Now let's go ahead and move on and try some three-step conversions. Okay, so the most common form of a three-step conversion is a gram-to-gram conversion. So in my example, if I want to create 50 grams of copper, how many grams of aluminum do I need? Okay, so this is an example where we're going to be starting at grams of our known, which in this case is going to be copper. And we're going to move to grams of our unknown, which in this case is going to be aluminum. So we're going to be using the molar mass of copper. We're going to be using the mole ratio. And then we're going to be using the molar mass of aluminum. Okay, so let's go ahead and try this. Starting with our known, which is what we want. We want to create 50.0 grams of copper. Now, my first step is that mole mass. Okay, I know that 1 mole of copper has a mass of 63.55 grams. Next up is the coefficients in that balanced chemical reaction. I know for every 3 moles of copper, put that one on the bottom because it's the one we want to cancel, I need 2 moles of aluminum. Okay. And then last but not least, grams of aluminum. I know every 1 mole of aluminum has a mass of 26.98 grams. So the moles cancel. And our problem becomes 50.0 times 1 over 63.55. So divided by 63.55 times 2 over 3 times 26.98, which gives us 14.15. So we'll go with 14.2 grams of aluminum are going to be needed. Okay, that's a 3-step conversion. Let's go ahead and try one more 3-step conversion, and then you will be masters of the mole map. Okay, so now we're going to go ahead and use a solution in a 3-step. So if I use 200 milliliters, milliliters. Molarity is in liters. I'm going to need one more step in my conversion factors here. This is going to be a 4-step conversion. You get a bonus one. But if we use 200 milliliters of a 1.5 molar copper solution and add excess aluminum, that just means I'm adding aluminum until all of that 200 milliliters of copper chloride react. How many grams of copper will I get? Okay, so let's go ahead and solve this out. I think I'm going to need even more room, so I'm going to go ahead and move this reaction up. Okay, and now let's go ahead and see. Our known is the 200 mils of the 1.5 molar solution. So we're starting down here on our mole map at volume of solution. Our known that we're talking about today is going to be copper chloride, and our unknown is grams of copper. So copper is what I'm going to be using again. Now it's asking for grams, so this is my ending point on my mole map, meaning I'll first use a molarity conversion, then I'll be at moles. I'll use the coefficients in the balanced chemical equation to relate the copper chloride to the copper, and then I will use the mole mass of copper again to get that to mass. Okay, but again, to get to my starting point, I need to be at liters, and I'm at milliliters. Do you remember how many milliliters are in a liter? Maybe. Okay, it's 1,000. So there are 1,000 milliliters per 1 liter. So that gets us to liters, which is our starting point. Then it's the number of moles over 1 liter, where that number is the molarity, 1.5 moles. So 1.5 moles over 1 liter. Then we're here. We're going to use the coefficients. Oh, we should add who we're talking about. We're talking about the copper chloride. 1 liter of the copper chloride solution and 1 mole of copper chloride. So then we know for every 3 moles of the copper chloride, I get 3 moles of copper. And that takes us to our last step, which is grams over 1 mole. 1 mole of copper has a mass of 63.55 grams. Okay, so we got 200 divided by 1,000 times 1.5 times 3 over 3 times 63.55, which gives you 19.06. So I'll go with 19.1 grams of copper. Okay, cool. Okay, cool. That's how we use a mole map.